Hello friends, welcome back to our channel. In this video, we are going to discuss about the process in Linux operating system. As part of this video, we are going to discuss about what is the Linux process, and we'll go through an example Linux process, and then we are going to see the creation of a Linux process, and finally, we are going to discuss about different types of Linux process. As part of this video, we'll go through various demos as and when required. So let's start with what is the Linux process. A Linux process is a program in execution. For example, we have a machine. It can be a virtual machine or a bare metal machine or a laptop where we install multiple programs or applications. Before running these applications or programs, they will be stored in disk. Until we execute this application or a program, that will be stored in the disk itself. If we start this application or the program, then it will be loaded into memory and corresponding instructions will be executed by CPU. So the execution of a program is called a process. So that means the difference between a program and a process is a programs or applications are just stored in the disk. The programs or applications which are in execution are called corresponding processes. These processes are created by the kernel, which is the brain of the operating system. Each process which is created in Linux will be identified by a process ID, and each process will have corresponding parent, and that parent also will have a process ID. So here in this case, parent will be identified by PPID, which is the parent process ID. Now let's go through a small demo about an example process in Linux operating system. This is the Linux operating system. Here, as of now, we do not run any Java programs in this machine. We can verify that by using ps command. PS command means process status. The PS command will be used to check the status of the processes which are running in this operating system. So here I am using PS. I am trying to list all the processes. I will explain what are these options E and F shortly. As of now, let's grab for Java. So as of now, we can see there is no process running related to Java. Now let us try to execute a Java program in this operating system. For example, here it is Tomcat. So Tomcat basically uses JDK or Java. When we execute Tomcat application, it will execute a catalina.jar file by using Java. Until we execute that program, Tomcat is installed in this machine in the disk, but it is not loaded into memory. Once we execute the Tomcat application, then that application will be loaded into memory, and then it would be executed by CPU. So let's try to execute Tomcat now. Now the Tomcat is in execution. That means a new process should be created for this Tomcat application. Let's verify that again by using ps command. So here we can see a new process is created, which is a Java application corresponding to Tomcat application. So here we can see the PID or the process ID of the process is 3543. That means this process is in execution, which occupies some of the CPU cycles as well as memory and so on. We can verify that by using top command. So this top command will show all the live processes running in this machine. So here we can see different processes are running. The process corresponding to Tomcat is Java. As of now, we can see it occupies around 9.2% of memory and also 0.7% of CPU utilization. So this way, the processes will be created when a particular program is in execution. In this demo, we'll use several commands to check the status of processes. For example, ps command. PS means process status. This will give the details about the PID of the process and the terminal with which the process is associated and the CPU time used, and finally the command which will be executed as part of the process. So if you want to get more details about the process, we'll use the same ps command but with more options. For example, E and F. So this E refers to the every process which is running in the system, and F refers to the full format of the process. So let's execute this. So here it is giving various details like the user which started the process, and the process ID, the parent process ID, and the CPU utilization, and the time when it is started, and the terminal session which is associated with this process, and how long the process is running, and finally the command which is being executed as part of the process. So with these details, if you want to get a particular process with a name, then we'll use ps-ef, and we have to grep with the name of the process. For example, grep Java. So that means it will list all the Java processes here. So here we are running the Tomcat application. So it has printed the details about the Tomcat process. So this is the PID of the process, and it has started with root user, and this is the command it is executing, and the details like the time when it is started and how long it is running, and the terminal associated with this, the parent process ID, and the CPU utilization. We can also use other options with ps command. For example, ps-aux. So this will give more details but in a different format. So here also we can see the details like the user and the PID, percentage of CPU utilization, percentage of memory utilization by the process, the virtual memory used by the process and the physical memory used by the process and the terminal associated with this process. So here the stat indicates different states of the process like sleeping, running and so on. I will explain about the states of a process in a separate video. The start indicates when it was started and time indicates how long it is running, and finally the command indicates the actual command which is being executed as part of the process. So we can use different options with PS command as per our requirement. So in this video mostly we will use the PS command with E and F options. If you want to see the live status of the processes, then we can use top command. Here it will show the live status of the process with different details. There are different other commands. We'll see those commands as and when required. Now let us see the creation of a process in Linux operating system. We have already seen how a user application, for example a shell program, will send the system calls to the kernel via the system call interface when we discussed about the basic Linux architecture. Basically, when we log into a terminal, a new process will be created for us which will run a shell program, for example a bash shell. So let's say this process is called P, corresponding to the shell program. So in this shell program, if we execute any command, then it will send a system call to the kernel via this system call interface. For example, if we run a command python3 example.py, then this shell program will send a system call called fork. So once this call is received by kernel, then the kernel will create a new process. So let's say this process name is C. For all the processes which are running in the machine, kernel will maintain the metadata about the processes in a collection of data structures which is called process table. So for process P, it will maintain a structure. Similarly, for process C, it will maintain another structure. So these structures are called task struct. So it will maintain a task structure for each of the processes. So each structure will contain the process ID, the memory information and the registers, the status of the process and file descriptors which are used to open the files, and also so many other things also will be maintained in each of the structures corresponding to that process. So here we have two structures corresponding to process P as well as process C. So initially for the fork system call, the structure corresponding to C will have the same information as the parent process which is corresponding to shell. So other than PID, most of the information will be similar to the structure contents corresponding to process P. So now the child process will start executing. Now it will try to execute this command. So for execution of this command, this child process will send another system call to the kernel which is exec. So in this exec call, it will mention what is the command it will run. Here it is python3./example.py. Once this call is received by the kernel, now the kernel will update the structure corresponding to the process C. Now this structure will contain completely different information when compared to the structure corresponding to P. So this will contain new memory structure, new registers, new status, new file descriptors and so on. So once this process table is updated, so the child process will try to execute the python3./example.py within this process. So it will keep on executing the process. Once the process is completed, now the child process will send one more call to the kernel with function exit. Once the kernel will receive this exit call, then it will clear off the structure corresponding to the process C. And then the kernel will inform the parent process by sending a signal. Until then, the parent process was waiting for the child process to complete. Then this will wake up and this will be moved to running state or runnable state. Then we can enter new commands in the shell. This way, when we execute any command inside a shell, that will create a new child process in which the actual command will be executed. Here, not all the commands which will create the child process. There are some commands which are built into the shell will not create a new process. Those will be executed within the process of the shell. For example, if we execute a command called pwd, this is a command which is built into the shell. So this command will not create a new process. But if we execute commands like Java or Python, so these will create new processes in which corresponding commands will be executed. So how to know which command will be creating a child process or not? So for that we use a command called type. So for type, if we give the argument as the command name, for example here pwd, we can see the output. So here it is showing pwd is a shell built-in. That means this will not create a new process. Similarly, if we type ls, so this is alias to some other. That means this is not a built-in command. So this will create a new process. So similarly, we can check other commands as well. For example, cd. So this is a shell built-in. That means it will be executed within the same process of shell. So let's say type python 3. This is not a shell built-in. That means this will create a new process. This way we can check whether a command is a shell built-in or not. Accordingly, we can know whether the command will create a new process or not. Now let us discuss about different process types in Linux operating system. We can classify the processes in different ways. For example, foreground process and background process. And also we can classify as parent and child process. And within the background process, we have different types of processes like batch process and daemons. And also in child processes, we can have orphan process as well as zombie process. Now let's discuss about each of these processes. Let's start with foreground process. So this foreground process needs interaction with the user. That means these processes will be started manually by the user by logging into some terminal session or from GUI and so on. So for example, the user logged into a terminal session and started a process P, which is a foreground process. So then the user needs to wait until the completion of this process to execute other commands in the same terminal session. And also this process will exist until the completion of this process or the completion of this terminal session. So that means if the process is running and if we close the terminal session, then this process will not exist anymore. So in summary, this foreground process will be started manually by the users and it needs interaction with the users, and this process will exist until the process completes or the end of the session. Now let's log into a terminal session and let's see an example of this foreground process. Here I have logged into a Linux terminal and here I have an example.python program. Let's check the contents of this file. This is a simple script. Here it will try to print the hello, and after that it will wait for 300 seconds or 5 minutes and then it will print hi. So when we execute this example.py as a foreground process, then it will create a process and it will be running in this terminal session for around 300 seconds or 5 minutes. After that this process will be exited. So until this process completes, we cannot run other commands. Let's see that. So let's try to execute this file now. So now it has printed hello and then it will sleep for 300 seconds now. We cannot execute any other command until the completion of this process. We can execute the commands in other terminal session and also we can see this process in other terminal session. So this is another terminal session. Now we can list the processes by using ps command and let's check the process corresponding to example.py. Here I am using ps command with options E and F and then I am grepping for example. So here we can see there is a process with PID 2892 is created and it is running. So let's wait for the completion of this process. The process is completed in terminal session 1. Now we can verify the process in the second session. Now we cannot see that process because the process is already completed. This way, when we run a foreground process, we have to wait until the completion of it to get the control of this terminal session and to execute other commands. Now let's discuss about the background process. Unlike foreground process, the background process can be run independent of the terminal session. Background process is non-interactive. That means these processes are run without user interaction. These background processes can be started automatically as well as manually. Once we log into a terminal session, if we start the background processes, these processes will run in background so that we can execute other commands in the terminal session when these processes are in execution. We can run the background process manually by logging into a particular terminal session and also we can run them automatically. In case of automatic execution, generally we can classify them as batch processes or daemon process. These batch processes will run at scheduled time by using some scheduler like cron scheduler and so on. The daemon processes are different type of background process and these will be started during the booting of operating system. These daemons will run continuously until we stop the process manually or until the shutdown of the machine. So now let's log into a terminal session. And let's see how we can start a background process. Let's take the same example for the background process as well. So here we have example.py. So let's execute this Python program as a background process. For that, we'll execute the same command. At the end of the command, we have to provide ampersand to run this process in background. So let's execute this. So now we can see a process with PID 2964 is created. So now this is running in the background. We can execute other commands as well. Let's say if I execute echo example. So now it has printed example. So this means we do not need to wait till the completion of this process to execute other commands in the same terminal session. Let's verify the process ID by using ps command. So here we can see a process is running with PID 2964 and it is running in the background. We can start multiple processes. For example, if I execute the same command, we can see another process is created, and let's verify the processes now. Now we can see there are two processes with PID 2964 and 2969. So this way we can run multiple background processes, and while they are running, we can run other commands as well. We can check the same processes in other terminal sessions as well. So here also we can see the same processes. So this way the background processes can be started manually by adding ampersand at the end of the command. Now we have seen manual execution of a background process. There are other types of execution in which we can execute automatically as well. For example, in case of batch processes, we can schedule a script to run at a particular time using the schedulers like cron tab. So in that case, we do not need to log into the terminal session to execute the script. That script will be automatically scheduled by the corresponding scheduler. So let's see that now. Generally, these batch processes will be used for different applications like loading of data into data warehouse tables from different sources. So this is one example. So generally these batch processes will be scheduled at non-business hours to reduce the load on the machines where these processes will be created and executed. So let's see an example now. So here we have the example Python program. Let us schedule this using cron tab to run at a particular time. So this is an example entry to execute the Python program. In cron, we have like multiple entries like this. The first entry will indicate the minutes, and the second entry will indicate the hours, and the next one is day of the month. The next entry is month of the year, and finally this entry is day of the week. So star 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 means they will run on each day of the month as well as week, and it will run at hours 13 and minutes 40. So this entry will run the Python 3 and the example.py, and the output will be loaded to corresponding test.txt file. Here 2 indicates the standard error and 1 indicates the standard output. So both standard error and standard output will be loaded to corresponding test file. We'll learn more about these things later. So now let us put this entry in a cron tab. Now let us see if any entries are there in a cron tab. So as of now, we don't have any entry. Let us check the current time. The time is 1:56 PM. We need to add the time accordingly. So here 1 PM means, so this should be 13, this is fine. And the minutes is 56. So let me add 59 so that it will run at 1:59. So to add the entry, we need to execute cron tab -e. So let us add the entry here. Now let us save this file. So the file is saved now. We can see the entry. Now the entry is present in the list of entries in cron tab. So this will be executed at 1:59 PM and the result will be loaded to test.txt. In another session, I have logged in and I have checked the date here 1:59. Now I have checked if any process is created corresponding to execution of the example.py. So here we can see a process is created at 1:59, and this is the command which will be executed as part of this process. So now let us see if this test file is created. So here we can see a test file is created. Let's check the file content. So now we can see it has printed hello and hi in this test file. So this means a process is created and it has executed this example Python script as part of the process, and the result is written to a test file. So this way we can schedule different batch processes at different times based on the requirements by using schedulers like cron and so on. We have one more background process which will be executed automatically during the booting of the operating system. So these are called daemons. So these daemon processes will be started at the boot time and they will continuously run until we stop them manually or if we shut down the operating system. For example, we have systemd daemon, which will create a process which is the parent of all other processes in the operating system. So we have various daemons like SFTPD for SFTP, SSHD for supporting the SSH protocol, HTTPD for web server, and so on. We can also create our own daemons by writing corresponding service files. So I would explain more about systemd and the custom services in a separate video. So this is about the daemon processes in a Linux operating system. Now let's discuss about the parent and child processes. If we start a new process, if this process is in execution, and during execution, if it tries to execute another commands, and if that creates another process, then this process will be called parent process, and the spawn process from this process is called a child process. For example, in the Linux shell, if we execute some command like a Python program, then that new command will be run inside a child process, and the shell program will continue to run in the parent process. Usually when a child process is created, then the parent will wait for the child process to complete. Once the child process is completed, then the child will send a signal to the parent process which is called sigchild. Then the parent process may continue to run, or it may execute other child processes. So in Linux, we have hierarchy of processes. So every process will be a child of other process except the init or systemd, which is the parent of all other processes. So here, this shell program can be a child of other process, and this can be a child of other process, and so on. And this process may be a child of systemd. So now we have two processes running, parent P and child C. If the parent process is terminated or exit before the completion of child process, then the parent will send a signal called sighub to the child process. Upon receiving this signal, usually the child process will be terminated if it is a foreground process, or if it is a background process, either the child process will be terminated or the init process, which is the parent of all processes, will become the parent of this child process. So if the child process continues to run after the termination of the parent process, then the process will be called as orphan process. So in that case, the process corresponding to systemd will become a parent of this child process. So when we start the child process, we may instruct the child process to avoid the sighub signal from the parent process. In that case, we need to execute the child process with nohub command. In that case, the systemd process will take out the child process when parent process is completed or terminated. So it is always advisable to use nohub if you want to run the child process even after the termination of parent process. So we also have another case. For example, we have P and C. So if child process is started from parent process P, and so if we don't have proper wait mechanism in the parent process, then after the completion of child process, that means the sigchild will not be received by parent. So in that case, even after the completion of child process, this child process entries will remain in the process table. So this process is called a zombie process or a defunct process. So to avoid these zombie processes, we need to have proper wait mechanism in the parent process so that it would receive the correct signal when the child process completes. So the difference between orphan process and zombie process is that orphan processes will continue to run even the parent process completes, and in case of zombie process, the child process is completed, but the entries of the child process will be residing in the kernel process tables. Now let us go through the demo to explain about the relationship between the parent and child process. Now I have logged into your Linux terminal. When we log into the terminal, by default, a process will be created with the corresponding shell program. Here it is bash shell process. Let's verify the process ID of the bash shell. For that, I am using echo $$ command. This is the PID of the bash shell. Let's get more details by using ps command. Here we can see 2235 is the process ID for the bash shell, and this is the child of the process with PID 2234. Let's get more details about 2234, and this process is corresponding to the su-session for login as root user. So let's get more details about 2233, which is parent of 2234, and this process corresponding to sudo su- for getting sudo privileges. Let's get details about 2232. So let's continue this until we get the parent process as PID1. So here we can see the SSHD, which provides the SSH session corresponding to process 732, which is a child of the process with PID 1. So this one corresponding to the process ID of the init process or systemd. We can also get this hierarchy by using pstree command. So if I execute pstree and providing the PID of 1, we can get this hierarchy. We have various child processes for systemd process, and we can see our pstree command is a child of bash, and we can see the entire hierarchy until we get systemd here. This way the parent-child process relationship exists in Linux operating system. So now if we execute commands in this shell, it will create a child process for us. So let's execute the Python command here. I'm running as background process. So now we can see a process is created with PID 2271, and this process is a child process of 2235. We can verify that. So here we can see 227 is the process corresponding to the Python 3 example py execution, and it is the child of the process ID 2235, which is corresponding to our bash shell. Now let us terminate this child process by using kill command. So the process is killed. Now let's verify the process again. The process is killed and the parent process will continue to run other commands. So we can run other commands in the parent shell now. Now let us see the effect of the termination of parent process on the child process. We'll see both foreground process as well as background process. Let's start with foreground process. So let's create a foreground process by executing this example Python program. So it is running. Let's see the process in the second session. So now we can see a process is created with a process ID 2662. Now let us terminate the first session and see what will happen to this process, which is running as a child process of this terminal session. Now let's see the example process. The child process also terminated. Now let's run some of the background processes. So it has created a new process. Let me log into another session. So in the new session, let's verify the process. Now we can see a process with PID 2693. Now let's terminate this terminal session. Now check the process again. So here, based on the implementation of operating system, either the systemd will take over the child process as the parent, or the child process may be terminated. So let's see here what will happen. Here we can see the parent process ID is 1, which indicates the systemd or init system has taken control of this process. That means it has become the parent of this orphan process. But it may not happen in some implementations of OS. So we have to be careful while creating a child process to run in background. So to ignore the SIG-hop signal sent by parent to child, we can use no-hop. So let's do that. Now let's run the same Python program using no-hop. Let's add ampersand at the end of the command. So now it has created a process with PID 2823. So let's verify the process again. So here we can see this process is also running along with previous process. So now let us terminate this session. So now we can ensure the child process will not be terminated because we have given no hop here. So which indicates the child process will ignore the SIG-hop signal that would be sent by this parent process when it is terminated. So let's terminate this session. Now let us verify the process again. So here we can see the init or systemd has become a parent for the process with PID 2823. Now let us take an example to explain these zombie processes. To create the zombie process, I have changed the example.py. So here we'll use the Python program to create a sub-process. That means the Python program will act as a parent process and it will create a new child process. So here we are using the fork function. That means the child process also will be similar, but the PID will be different when compared to the parent process. So here once the child process is created, we are checking the PID. If PID is greater than, that means it's a parent process. Then it will print the parent process PID and also it will print child process PID fork. Once the forking is done, then the parent process will wait for the child process. But here we are not putting any wait function. The second condition is to check if PID is equal to 0. That means it will check for the child process. So for the child process, this will print this message, and after that it will sleep for 50 seconds and then the child process will exit. So once it exits, it will send a SIG child signal to the parent process. since we did not put any wait function here, the parent process will not catch the sigchild signal which is sent by the child process. So that means the entries of the child process will not be cleared from the process table even though the child process is terminated. So let's copy this in an example file and execute this program. I have copied to example1.py here. So now let's execute this example1 Python program. So now we'll have two processes. One is the process corresponding to example1 and also the child process of this process. So let's execute now. So here we can see the parent process with this PID is running and it has forked a new process with PID 3071 and this child process will exit after 50 seconds. Now let us verify the processes using ps command. So here we can see there are two processes. One is the parent process with PID 3070 and the child process with 3071. So this 3071 will be terminated after 50 seconds. So once it is terminated, it will send the signal to the parent 3070, but it will not take the signal because we have not put the wait function. That means after termination, this 3071 will become a zombie process or a defunct process. So let's wait for 50 seconds and then we'll check again. I have checked after 50 seconds here. Now we can see the child process 3071 is terminated, but still the parent process 3070 is running. Now let us see if any zombie process is created which is corresponding to the terminated child process. So here we can see there is a process 3071 which is a defunct process. So this process is the zombie process or the defunct process. The entries corresponding to this process are still present in the process table. So to avoid this zombie process, we need to have the wait function in the program corresponding to parent process. So this is about the zombie processes in Linux. So in this video, we have gone through what is a Linux process and we have seen different examples of Linux process and we have gone through different commands which can be executed to check the process status. We also have gone through the creation of a process and various types of Linux processes in detail. In the next video, we'll go through different states of the process and various signals which will be used to control and manage the processes in Linux. I hope this content is useful. If you like the content, please like, share and subscribe. Thanks a lot for watching.